last time we talked about equivalent functions. And so essentially we see these two graphs here. These are equivalent functions. Equivalent functions are functions that are identical everywhere except at finitely many points. So here, you know, the graph on the left and the right, they're basically identical except for at 3 points they differ. Now, the key is that it should be finitely many. It could be 10,000 points as long as it's finitely many. So, so before we get into the convergence, there's one little subtle point that needs to be fleshed out. And this is a very subtle technical detail. You know, it's actually counterintuitive. So before we get, and to get into that technical detail, I need a definition. So I need to define the notion of what it means for one set to be dense in another. So suppose B is A and B are sets, and that B is contained in A. So, you know, the usual thing is we always kind of draw a circle and say, oh, this is the set A. And then now I have a set B contained in there. So we say that the set B is dense in A. And so here's the word, technical word here is dense. If any point little a in A can be written as a limit of points from B. So let me show you the notation here. So this is the definition. If for any A in A, there exists a sequence of points B sub n in capital B such that that sequence converges to A. So, you know, when I draw my, so it's hard to imagine. You kind of have to use, you know, you kind of have to think a little abstractly. So if this is the set A, then set B, you know, when I think about it being dense, if I try to think of a picture, is these little tiny blue dots kind of make up set B. And they're all over A. And now if I pick a point here in A, I can find a sequence purely involving points in B. So I can find a sequence only involving points in B that'll converge to that point in A. And this is for any point in A. I can always find a sequence of points purely that are in B that'll converge to A. So in a weird way, the set B is kind of evenly distributed throughout the set A, in that any point in A can be seen as a limit of points from B. So there's a very famous example of this, and this is kind of abstract. The notion of dense sets, you know, the concept of density, that's one that you study in an analysis class. It's a little tricky. So there's a very famous example, you know, and I say it's a famous example. In fact, it's a fundamental result of our mathematics. And it's the result that the rational numbers are dense in the real numbers. So let me explain some definitions so that that sentence makes a little more sense to you. So when I say the rational numbers are dense in the real numbers, so at the top of it, what I'm saying is any real number is the limit of a bunch of rational numbers. But here, let me just build up. So if we start with the set of integers, which is 0, plus minus 1, plus minus 2, we can define the rational numbers to essentially be the set of fractions of integers. You know, the important thing is the rational numbers are fractions of the form P over Q, where P and Q are integers. So if I do, you know, pi over 2 is not a rational number because pi is not an integer. So like 1/2, 3/4, 7/6, you know, all the kind of nice numbers that we liked in elementary school when life was kind of simpler. So we denote the set of rational numbers, the set of all essentially fractions made up of integers where of course the denominator cannot be 0. We denote that as Q, this fancy Q here. Q, you know, for the word quotient. So now what we're saying with this density result, and so this is a famous result proved by Dirichlet, is that any real number, so the real numbers are basically made up of rational numbers and numbers that are not rational numbers, okay? So numbers that are not rational are called irrational. So, these are major results that took a long time to prove, and I'm just kind of chatting about it like it's easy, but it's not easy at all. So, it was proven that the real numbers are made up of the rationals and the irrationals, and the rationals and the irrationals have no intersection. Their intersection is the empty set. And then it was also shown that if you pick any irrational number, like pi, we can find a sequence of rational numbers that converge to that irrational number. When we talk about pi, it's important to realize that, there's no such thing as finding all the digits of pi. That's not a thing, because the digits go forever. And when I say forever, I mean more time than there is in this universe. These are conceptual things that don't need reality to exist. So it's important, to kind of realize there's this weird counterintuitive thing happening here, that every irrational number is a sequence of rational numbers. So what does that mean? You pick any irrational number like e or pi, I can get as close to e or as close to pi with a rational number as you want, but I can never get to pi. I can approximate it as accurately as you want just by adding on more terms of my series approximation here. I'll talk about the series that I have here on the slide in 1 second. So that's the thing. It's really counterintuitive that the number is irrational, but you can approximate it as closely as you want with a rational number. That's kind of, and we're going to do the same idea with functions. So now let me talk about the series here. So from the max series of e to the x, if you replace x with 0, we come up with a series expansion for e. Now, e can be proven to be irrational, e, the Euler number. And so on the left-hand side, what you should really notice now when you look at this, on the left-hand side, we have an irrational number. On the right-hand side, remember that a series is a limit. It's actually a special type of sequence. A series is a sequence of partial sums. So here on the right-hand side, we have a limit of a bunch of rational numbers. These partial sums right here, these are all rational numbers. It's a finite sum of rational numbers. They're all fractions of the form 1 over an integer. And so there's something innately counterintuitive here in the sense that on the one side, I have an irrational number. On the other side, I have a limit of rational numbers. And in between, I have an equal symbol. Yet the rationals and irrationals, their intersection is empty. There's no number that's both rational and irrational. So yeah, we just accept it. That's what you do as a mathematician. You just go, oh yeah, it's beautiful. I get it, sort of, not really, Sean asks if B is dense in A. Is it also dense in any subset of A? Yes, Sean, I believe that's a correct result. Absolutely, and I agree with that statement. So now when it comes to Fourier series, we have a similar thing going on here. Okay, so with Fourier series, so let me set the stage for Fourier series. First of all, let me define a trigonometric polynomial. A trigonometric polynomial is a finite sum of this form. It's not a polynomial in the sense that you're raising it to powers. It is in the sense that we have multiple wave numbers. So here the wave number takes the place of the power, the exponentiation, in a polynomial. So you can think of this as the nth partial sum of a Fourier series. That is to say, if we send capital N to infinity, then we get, what we call a Fourier series. If I send these two characters, if we send this in a limit, then you get the Fourier series. if you send it to a limit. Okay, so these are the nth partial sums. Okay, so here's the counterintuitive result that I want to talk to you about. And I feel that in the notes on Fourier series that are posted, this point is not discussed properly. In fact, I think there's an error in those notes. But anyway, here we go. So here's how I believe the information is organized, and I have some reference for you at the end of this set of slides. So the claim is, what can be proven is that every continuous function, so let's read this slowly, every continuous function defined on a closed interval is the limit of trigonometric polynomials. Another way to say that, using our mathematical language, is the set of trigonometric polynomials is dense in the set of continuous functions. Now, here's the very subtle point that I want us to all appreciate. I'm not saying every continuous function is a trigonometric polynomial. I'm saying every continuous function is the limit of trigonometric polynomials. So we can approximate the continuous function as accurately as we would like with our trigonometric polynomials by just using more and more terms from the series. But the function we're approximating is not a trigonometric polynomial. And by analogy, so, the discussion about uncountable and countable numbers and sequences of rational numbers approaching irrational numbers, that's by analogy. Just like E, which is an irrational number, we can express as a sequence of rational numbers, will prove any continuous function on a closed interval we can write as a sequence of trigonometric polynomials. But I'm not saying, every continuous function is a trigonometric polynomial. All righty, folks. So one last comment here, and then we'll move on with our lives. So if you remember, back in 1873, I think it was a Wednesday, actually, old Dubois-Raymond gave an example of a function for which the Fourier series at 0. So he's evaluating the Fourier series at x equal to 0. It doesn't converge. And in fact, there are examples of continuous functions defined on a closed interval where the endpoints meet so that the periodic extension makes sense, whose Fourier series diverge at infinitely many points inside the interval. So the point of this statement is that it's not just you pick any function and find its Fourier series and everything's going to be hunky-dory. Hunky-dory is a term we used back in 1873. I'm trying to bring it back. So this is why we kind of need some extra requirements. It's not enough just to say the function's continuous. We need some extra requirements on f of x before we can, so that when you find the Fourier series of the function f of x, what you get is something meaningful, something that converges to the thing that you started out with. So now I'm gonna talk about these restrictions, on the next lecture. We're really close to the end here. So let me make one final comment about the Fourier series, because I said the Fourier series does not converge to the periodic extension. So I want to get to what does the Fourier series converge to. Okay, so there's one final little very interesting fact about the Fourier series that we should talk about. Then we can talk about the convergence theorems, and then we can just start solving PDEs. Okay, so we're really about to turn a corner here, folks, and you're doing great. So here we go. So here's the setup. Suppose we have a function f of x, and you remember the periodic extension will be well defined if and only if the function defined on this closed interval minus L to L, that those endpoint values are equal. Okay, so in general, though, I want to talk about the Fourier series. One of its famous properties is that it does what we call smoothing. So the Fourier series, one of its famous beautiful properties is that a convergent Fourier series does what we call averaging or smoothing of the original function. So I want to motivate this with math. Okay, so first of all, let's suppose we have a function f of x defined on the closed interval minus L to L, And now I'm going to assume that the function is equal to its Fourier series. That is, the Fourier series converges. And on the interval minus L to L, the Fourier series equals the function f of x that we use to generate it. So notice that the Fourier series on the right-hand side is 2L periodic and continuous. Every term on the right-hand side is 2L periodic, including the constant. And every term is continuous. And so here, you add them up, they're still 2L periodic, and sums of continuous functions are still continuous. Okay, so now we're going to use these properties, okay? So first, let's see what's going on at the endpoints. So by the periodicity, I know the Fourier series at negative L if you add 2L. So that's the periodicity. This is a 2L periodic function. So every time we traverse a distance of 2L on the input axis, it repeats the output on the output axis. So if you add 2L to negative L, you get L. By periodicity, the Fourier series of f at negative L is equal to the Fourier series of f at L. Okay, now math trickery. Add the Fourier series of f evaluated at L to both sides. Why do I try to write? I'm pretty sure I'm traumatizing you right now. Add the Fourier series. Oh, God, I'm just going to go to the next thing. So here, be very careful now. Just how did we get from one equation to the other? So from this equation, what I did was I added one here, Fourier series of f at L. And on the other side, we already had one copy. So when you add, you get two of them. Now, what I'm going to do is divide both sides by 2. What I want to do is isolate this term. So I'm going to divide both sides by 2. I get the Fourier series of f evaluated at L is this average of the Fourier series of f at negative L and the Fourier series of f at L. And since I'm assuming here the Fourier series is converging inside the closed interval, here the Fourier series at L turns out to be the average value of, the value of the original functions at the endpoints negative and L and L. So remember, I said that the Fourier series isn't just the periodic extension. So this is how the Fourier series is more than just a periodic extension. At these, essentially, you can think of these as a jump discontinuity if you wish. At these jump discontinuities, it's actually averaging and plotting the point in between. And what happens at a removable discontinuity, we have a similar type of phenomena. At a removable discontinuity, so here, what does that mean? We've got, so suppose if this is the graph, I've got a hole. And now I'm assuming the x value where that's happening is C. I just picked, so C is where we have our removable discontinuity. I don't know, I just picked the letter C, but maybe that's a bad letter. But so that on the x-axis, it's where we have a removable discontinuity. And so now we're going to play sort of the same game. Last time we used the periodicity. This time we're going to use the continuity. So remember, the Fourier series is continuous. So the Fourier series of f at C can be seen as the limit of f of x as x approaches C from the right. So that's this limit here, from the right. This limit here from the right. And it's a removable discontinuity. So the limit from the left and the right are actually equal. So the Fourier series of f at C can also be seen as the limit from the left. Now, I just want to do a simple thing, add the top equation to the bottom equation. So add this equation to the bottom equation. Add the left-hand sides, add the right-hand sides, and then divide by 2. When you just add them, so when you initially just add them, you get, a 2 here on the left-hand side. So just add these two equations. Fourier series of f at c plus Fourier series of f at c is 2 Fourier series of f at c equal to the sum of the right-hand limit and left-hand limit on the other side, and then divide by 2. And so now we see at the removable discontinuity, the Fourier series, which is a continuous function, will actually average. It'll average the limit from the left and the right and divide by 2. And what that averaging will do is it'll fill in the hole. So if there's a hole here, by looking at it's gonna take this limit from the left. It's gonna come in on the right here as a limit. Remember, the limit never gets to its goal. It's just like, it can see where it's going, but it never gets there. And you look at the limit from the left, add the 2 points and divide by 2, and then this point gets redefined in the Fourier series as that averaging. And the removable discontinuity will get smoothed over and filled in.
Dr. Bott?
Yes, sir.
Does that imply that your removable discontinuity doesn't have a value somewhere else? X equals, Y equals 100.
It could, and the Fourier series doesn't care.
Okay.
Yeah, the Fourier series won't see that.
Okay, so that doesn't knock off the averaging of it at all?
No, it doesn't, because we're using limits, the value at the point never comes into play.
Okay, that makes sense.
Yeah, and so one point of view, is that this is really a nice property of the Fourier series. And one example is traditionally given is if you have data that's maybe like a function, but your data has holes in it, due to static or something, you have finitely many holes in it. Applying the Fourier series to it will fix the gaps. It'll fix those holes, and the Fourier series will be maybe a nicer continuous version to work with, So this is one of these, it's just what it is. So we're here kind of cataloging the behavior of the Fourier series. Okay, so let me just show you a quick example, a quick little numerical example. And in fact, this analysis is true at every point, not just at a removable discontinuity. It's averaging the left and right hand limits, of the function at every point. Okay, so here I did the Fourier series of f of x equal to x on the closed interval minus pi to pi. So that's graphed here in this lighter shade in the back here. And then I did the periodic extension. So that's what that is. I didn't draw this part. I kind of just drew the extra, that you would have. And so now here's the Fourier series that I calculated. I don't know if we did this in a homework, but here's the Fourier series I calculated. And now I'm slowly starting. So first I start with a one-term approximation, and you can see the one-term approximation is just a sine curve. And now I'm going to slowly start adding terms. Okay, so this is a 3-term approximation. Oh, by the way, even in the one-term approximation, look where this point goes through. In between right here, it's not a coincidence. Our one-term approximation is averaged. If you take the average of pi and negative pi, divide by 2, you get 0. I should have put some removable discontinuities in this thing also, now that I think about it, and I don't know why I didn't do that. And I'll do that maybe for next time. So here's a 3-term approximation. Here's a 4-term approximation. Oh, no, sorry, 6-term approximation. 21-term approximation. And in every case, you see it's doing this averaging thing at the endpoints here. It's continuous. I should have put a removable discontinuity in this thing. It would have fixed the it would go through it. You can see the Fourier series is totally, and I shouldn't say Fourier series. I should say you should see the Fourier polynomial is totally continuous. In theory, when we send n to infinity, in theory, this is the hard part to understand. When we send n to infinity, the Fourier series will converge to the original function f of x that's not necessarily continuous everywhere. That's the hard part. Like here, if I send n to infinity, in theory, this part will, whoops, sorry, let me try that again. In theory, this part will disappear. This part will disappear. and we'll just get back a totally diagonal line that looks like our original function. That's when you send n to infinity. You know, and that part to me is counterintuitive. Okay, so Evan, do you have one?
Yeah, I was kind of confused about this point. So these Fourier polynomials, so these trigonometric polynomials converge to this function even if it has a discontinuity at infinity, right?
Yeah.
Okay.
Yeah.
So there's a theorem in analysis that says if you have a uniformly convergent sequence of continuous functions, that the limit of this sequence of functions is also continuous. So how does that come into play here?
So here, I mean, I guess that's true if this was uniformly convergent. So we'll talk about I don't know for this function, I don't know if it is.
Okay, but there's some cases where the trigonometric polynomials are not a uniformly convergent sequence.
Yeah, so actually, I know here this is not uniformly convergent. Actually, thank you for reminding me, because of the Gibbs phenomenon. So here you see there's a little extra bump right at the discontinuity. That's called Gibbs phenomenon. And if we have uniform convergence, then there's no Gibbs phenomenon. And here the problem is the points here, Evan, are converging faster than the points here. For uniform convergence, we'd get uniform convergence, right? You'd get all the points would approach their limits at this essentially the same rate. So yeah, here this is not a uniformly converging, the partial sums of this Fourier series are converging, but not uniformly.
Okay, so that little spike that happens near the discontinuities, even if we went out to like a Googleplex terms or whatever, that would still be there.
Exactly, that never gets better. It never gets better. So you can see.
Except in the limit, right?
Except in the limit, you know, which again, that part I want to see it, but we'll never see it, right? Because as humans, we're never gonna, I don't know. I'll think about it some more. So yeah, I wanted to give you some references for this. I posted this. This is really like very difficult to read. And the relevant parts are the first couple of pages. There's some historical remarks, but I just wanted to give you some references. Certainly it's optional, you know, I wouldn't worry about it if you're not too concerned. And then I also wanted to give the counterexample by Dubois is in Bleeker's book. So that's why I've given you that. So let me now switch over and start talking about the convergence. Let's actually discuss the first. So there's essentially two theorems. There's a result today, result Friday, and then Monday we'll talk about the uniform convergence and absolute convergence and stuff like that. So all right, let me switch over. So these are the notes for the next set of notes on Fourier series by Harvey Seeger, and I've posted these slides on Canvas. So, and you know, one thing I'll mention is that you know, note that every slide has a unique number. So if you ever have a question on a specific slide, you can always reference it that way. So I want to just do some basic definitions so that we can say exactly what the restrictions are on the Fourier series. So just to remind you, remember we say a function is continuous at a single point x equal to a if the limit of f of x as x approaches a equals f of a. So now let's just review our calculus. This is saying three different things, right? First of all, remember the limit on the left-hand side is a two-sided limit. So this is saying, you know, the limit from the left is equal to the limit from the right. That's the first thing it's saying, that the left-hand side exists. The second thing it's saying is f of a is defined, that for the function, you can plug in a and you get an actual number. F of a is not plus or minus infinity. So, you know, this is saying three things. One, the limit on the left-hand side exists. Oops. The limit on the left-hand side exists. That's the first thing it's saying. The second thing it's saying, f of a exists. The expression on the right-hand side exists. And then finally, the third thing it's saying is that the expression on the left and the right are equal. So there's three different comments being made here. The two-sided limit exists. The function at the point exists. The two-sided limit equals the function at the point. Okay. So we can weaken this definition by defining a notion of piecewise continuous. So this is when the function is continuous at all but finitely many points. So here you might have a jump discontinuity or a removable discontinuity. We're not allowing infinite discontinuities. That's a kind of important part of our theory. If you want to see it as a limitation of our theory, so be it. It's just, if we allow infinite discontinuities, the Fourier series isn't going to work out because the integrals aren't going to work out. The integrals are going to blow up. And we require that at the endpoints, we don't have any blowups. So here, it's a subtle statement here. At the endpoints, we say the limit from the right at A, which is the left endpoint. So maybe let me just draw this here. So here I have, here's A and B. Here's A, here's B. So at A, we're looking at the limit from the right, and this has to exist. It can't blow up to infinity. And at B, we're looking at the limit from the left, and it has to exist. When we say the word exist, it means it has to be a finite number. Now, be very careful. I'm saying the limit has to exist. The function doesn't have to be defined at the endpoint. Right? Just a limit approaching the endpoint has to exist. So we're not allowing any infinite or blowups to infinity or negative infinity. That's the first thing for this to work. So now we can define what we call in this class piecewise smooth. That's the terminology we will use. If different books use different terminologies, a more general term might be to call it piecewise C1. But we'll just use piecewise smooth in this class. So a function is said to be piecewise smooth on a closed interval AB if the function is piecewise continuous and if the derivative is also piecewise continuous. And I can tell you that these are essentially the two requirements we need to get well-defined Fourier series. There's one more little piece of information we need. This is not everything. I still need to do that averaging, and still need to make sure if it's not equal at the endpoints, we're gonna do this averaging. So, okay, so if the original function f of x is continuous, but f prime of x is piecewise continuous, then we can say f of x is continuous piecewise smooth. The word smooth typically in analysis is reserved for all orders of derivative. So that's why to me it's a little peculiar, the terminology, although I have seen this terminology in more than one book. I like piecewise C1 better, but we'll use piecewise smooth just to be consistent. Okay, so piecewise smooth here just says f is piecewise continuous and f prime is piecewise continuous. Note that f and f prime might have discontinuities at different places. That's okay. We can create a common set of discontinuities of either f or f prime. Let me switch over here for 1 second to the document camera. And so here I drew a picture of what might be a piecewise smooth function. So you say f of x is piecewise continuous. You can see the derivative will not be differentiable right here. And so here, I can make a list of points. So I'm going to now call this x1, I'll call this x2, and I'll call this x3. I can compile a list of points where either the function or the original function, either the function or its derivative, are not continuous. And we can, now when we do our integrals, we can take our integrals as partials between these regions. And if we're integrating the function or the derivative, those integrals will be well defined. And why would we want to integrate the derivative? Let me show you. In the proof of the, of part of the convergence theorem, the derivative of the function makes an appearance. And that's why we're making these requirements on not just the function, but the derivative as well. So, okay, so let me return to the slides. And so here I make a comment that is, if f prime is piecewise continuous, then f of x is also piecewise continuous, and I say why. And I think the correct answer is that differentiability implies continuity. So I guess, you know, if it's differentiable on the pieces, then on those pieces where it's differentiable, the original function should be continuous on those pieces. I don't even know if I need to mention that. Okay, so quick example of functions that are, you know, piecewise continuous and that are not piecewise continuous. There are many functions that are not piecewise continuous, especially because we're requiring finite limits, right? So obviously, like 1 over x on the interval -1 to 1 is not going to be piecewise because the right and left limits at 0 are infinite, and we're not allowing any infinite limits, right? So you remember the graph of, so here, 1 over x. And now we're in the limit. Let's just, okay, yeah, it just became a mockery. There's 1 to -1, I don't know. And so right here, you know, these infinite limits, we don't allow that for the definition of a piecewise smooth function. You can look at sine of 1 over x. There's no infinite limit. Sine is bounded, right? Always between -1 and 1. But at 0, this limit is just not defined. Limit of sine of 1 over x as x goes to 0 is just d and e. It does not exist. It's just not, because 1 over 0 is not defined. If you go limit from the left and the right, you know, 1 will go to sine negative infinity, whatever that means, just oscillates forever. And then from the other side, sine to plus infinity, that just oscillates forever. So here, this is not going to be piecewise smooth. Take absolute value of x to the 1/4. So first, I think it's really important to think about how do we work with this function from a calculus point of view. So, you know, if it's been a while, we use the definition of the absolute value. Remember, if x is greater than 0, if x is greater than 0, you just replace the absolute value with just x. So here, if x is greater than 0, I just replace the absolute value of x to the 1/4. If x is less than 0, then you replace the x symbol with a -x. You throw parentheses around it, put the 1/4. Don't separate these terms, because then you're going to get complex numbers. And don't get confused here. Negative x is actually positive, right? Because x is less than 0. So f of x, no problem. F of x is definitely, you know, piecewise continuous. There's no issue. Actually, I think f of x is just flat out continuous, right? So it agrees at 0. But if you take the derivative, and so for the derivative up here, I'm using just a straight power rule. For the derivative negative x to the 1/4, I did a chain rule. Okay, derivative of the outside times the inside. Derivative of negative x is minus. That's where this minus sign is coming from. And here, since we have a negative exponent, we see that the derivative is not going to be piecewise continuous. So here, the derivative, f of x is piecewise continuous. F prime is not piecewise continuous. So f of x is not piecewise smooth. I should have added that here as another line, that f of x is not piecewise smooth, and I'll add that. So here, the conclusion of this example is the original function f is not piecewise smooth. It is piecewise continuous, but it's not piecewise smooth. Consider the regular absolute value function. Here, both the function and its derivative are piecewise continuous. The original function is actually continuous. The derivative is piecewise continuous. It has a jump discontinuity at 0. And here, the original function is piecewise smooth. In fact, it's continuous piecewise smooth. Okay, folks, we're going to now start talking about when Fourier series converge. Okay, so here, for a series, of course, first thing we need is the absolute value of a sub 0 has to be finite for the Fourier series to make sense, first of all. Okay. Second thing is, for a series to even be in the running for convergence, we need the coefficients to go to 0. Otherwise, we can use this, you know, divergence test for series. And this is exactly why we reviewed all that series stuff in the first week. For the divergence test, we know if the a sub n's don't go to 0, then the series will diverge. Okay, so that's the first thing we're going to prove. So we'll prove this, the coefficients go to 0. Okay. So here we're going to put two restrictions on our function. So these are now restrictions. These are the restrictions on functions we're going to place. And these are the only kinds of functions we want to look at Fourier series for. So if the function that's defined on minus L to L, if it agrees at the endpoints, then the only restriction I have is that we require its periodic extension to be piecewise smooth. So we require the periodic extension of the function to be piecewise continuous and the derivative to be piecewise continuous. If the endpoints aren't equal, then we're going to redefine the function. Some books use the term adjust. Some books use the word normalize. I'm just going to go with adjust or redefine. We're going to redefine or adjust the function at the endpoints and redefine the new endpoint value to be the average of the old endpoint values. And now, because this is math, I'm going to introduce some notation. We denote the adjusted function as f bar, right? So we don't want to do the Fourier series on a non-adjusted function. We're only going to do Fourier series of the adjusted function. And now we require restriction number 1 to be true of the adjusted function. That is, we require the periodic extension of the adjusted function to be piecewise smooth. And now it's really annoying. The periodic extension of the adjusted function looks like f bar tilde. Okay, but for the sake of sanity, I'm not going to write the bar. I'm just going to write f tilde, and from here on in, f tilde will represent not just the periodic extension, but the periodic extension of the adjusted function, where it's fixed, where it's averaged at the endpoints, so that the endpoints are equal and they're equal to the average value. Note that if we use this definition, in this case up here where the points are equal, there's no contradiction. If f of negative L does equal f of L and you add the two and divide by 2, and if you average them, you just get back the same y value. So you can think of us as using this definition always, that we're always averaging the values at the endpoints, whether they're equal or not, because it ends up to being, the same thing at the end of the day, whether they're equal or not. So, all right, folks. So now I'm going to show that the coefficients go to 0. Okay. So here, I won't do the whole proof. I'll do, it's pretty quick actually. So, and it just uses integration by parts, but here, let me do this first half here. So the first thing is that functions that satisfy restriction number 1 and restriction number 2 form a vector space. So what does that mean? If f and g satisfy restriction number 1 and 2, then any linear combination does as well. So if you add two functions that satisfy restriction 1 and 2, then the sum will also satisfy it. If you take a function that satisfies restriction 1 and 2 and multiply it by a constant, that new function will also satisfy restrictions 1 and 2. Okay, and I'll let you think about that. So now, the second claim is that if a function satisfies restriction number 1 or number 2, there's a finite positive number such that the absolute value of the periodic extension is less than that number for all real numbers. This shouldn't come as a surprise to anyone, because we're not allowing the function to have infinite discontinuities. We've taken out any place where the function can have an infinite discontinuity. So the only other thing left is that the function must be bounded. So, so here, the important thing to keep in mind is that we're on a closed interval. We don't have any open points here. And the function is piecewise continuous on this closed interval. So at every point, what we can say is that every point there's not going to be an infinite limit. That's one thing I can guarantee. And from analysis, don't worry about this part. From analysis, we know that closed and bounded intervals like this are compact, and that continuous functions and piecewise continuous functions will be bounded on compact sets. Okay, but here the idea is we force the function to where it can't blow up to infinity. Okay, so the continuity forces f of x to essentially be finite, and the range of the function will essentially be bounded because of the restrictions we've put on here, the closed interval requiring the continuity. And so we will be able to find a positive constant that bounds the function in the original interval. Here's where we're using the properties of being on a closed interval. But because it's periodic, it just repeats itself. Periodic just means the function, it just looks the same, right? Ever so often, every 2L to the left and right, you'll just get the same picture. So here, the function, the periodic extension of a bounded function will also be bounded and will have the same bound. And so this completely is a result of the fact that we've forced the function to be continuous. And so, that's just a fact that we will be free to use in this class, that if we're looking at a function that we force to be continuous or piecewise continuous on a closed interval, then we can assume that it'll have a bound. And it's from this larger result in analysis that continuous functions over compact sets are bounded. So I'm gonna stop here, but I wanted to show you the result for next time. And it's not very difficult. So these aren't difficult results to prove. And so I'll knock these out. So the next result I want to prove is that the coefficients of our Fourier series. So here, these are the coefficients of our Fourier series. They all are bounded if the function f of x satisfies restriction 1 and 2. So we'll take that bound we found on the previous slide and show. So this is a big step towards showing that the series, these coefficients aren't blowing up to infinity. Remember, I want to show that these coefficients go to 0. So this first step here shows that they're bounded. And then the second step, using integration by parts, I'll show you that when we send n to infinity, not only are these things bounded, but when we send n to infinity, they'll go to 0. Okay, so try to keep the big picture in mind here, that we're trying to show the coefficients are going to 0. Otherwise, by divergence test, this whole thing will diverge. And so here, the first step is we'll show that they're bounded. And then the next time I'll do integration by parts and show you that it goes to 0. And then next time also, we'll start the big, messy convergence proof. Okay. All right. I'm going to stop right here because I just only have 2 minutes. So I'm going to stop right here. Thanks for your time, everybody.